Okay, so we are in section 3.2. This is the mean value theorem. We'll kind of break down what that means. If you actually just look at the words, you should be able to hopefully figure a little bit of it out. It's actually one of the more important theorems that we cover, specifically for the AP test, because they tend to utilize this theorem at least a couple of times, if not more, on the AP test. But as far as the theorem itself is concerned, again, I think it's something that just makes sense, especially if you understand what the words mean, because math people aren't extremely creative. When we call things what they are, we just kind of name them what they are usually, unless it's named after a person. For example, the first theorem we're going to talk about, which is not quite as important, but it's a good stepping stone to the mean value theorem, is called Rolle's theorem. Okay, obviously it was named after the person that came up with the theorem, and his last name was Rolle. So they named the theorem after him. And it says, let f be a function that satisfies the following three hypotheses. 1, f is continuous on the closed interval from a to b. So it has to be a closed interval, and f is continuous on that interval. F is differentiable on the open interval from a to b. So it just doesn't have to be differentiable at the endpoints. And the last one says that f of a equals f of b. And remember, f of something is a y value, so it's just saying that the y value at the first endpoint is the same thing as the y value at the second endpoint. So basically, this curve starts and stops at the same y value. If that is the case, then there is a number c in between a and b such that f prime of c equals 0. Okay, so let's take a look at these two specific examples. So in the first one, we're going to clearly show that this is A and this is B, so the endpoints are closed. And it certainly does look like, it's hard to tell here, but it certainly does look like those y values are the same. So this y value is the same as this y value, which basically means this. You have a horizontal line or a horizontal segment that can be drawn between A and B. And because of that, someplace else on this curve, because it fits the criteria, 1, it's continuous from A to B, 2, differentiable between A and B because there's no issues there, and f of A and f of B are the same. So if that's the case, it's telling us that at some point on that curve, you're going to have a horizontal slope, or if f prime of c equaling 0. And it looks like right there at the top, we have what appears to be a horizontal slope. So the x value associated with that down here would be your c value. And that would be guaranteed by Rolle's theorem if those things are met. Continuous, differentiable, and f of a equals f of b. Okay, so now let's take a look at the second example. So again, we're going to definitely close this off and say that that's A, that's B. It is clearly closed. It's definitely continuous. The biggest difference here is that this is not differentiable, because once again, it looks like f of A and f of B are the same y value. But right here, this is not differentiable on the entire interval. And because it is not differentiable on the entire interval between A and B, we cannot guarantee that at some point on that curve, we're going to have a slope of 0. As a matter of fact, you cannot find a point on this curve anywhere that there is a slope of 0. There's a slope of 0 in between the two endpoints, but not on the curve itself. Okay, so in essence, that's basically Rolle's theorem. Okay, and it's really kind of again, it's a stepping stone to the mean value theorem. It's a special condition, one special circumstance of the mean value theorem, which we'll get to. But let's go ahead and practice one of Rolle's theorems. So it says, let f of x equals 4x squared minus 20x plus 29. First, we want to show that f satisfies the hypothesis of Rolle's theorem on the interval from 1 to 4. Then we want to find all the c's, or the c values, in between 1 and 4 such that f prime of c equals 0, and illustrate that graphically. So the first thing it wants us to do is to verify the hypothesis of Rolle's theorem works. Well, it's a polynomial, so it's continuous on the closed interval because they gave us a closed interval from 1 to 4. Is it differentiable? Once again, it's a polynomial, which are differentiable everywhere. So it will definitely be differentiable on the open interval between 1 and 4. Then we have to check, does f of a equal f of b? Well, let's see. F of a is f of 1. A is your left endpoint. So if I plug 1 in there, plugging a 1 in is going to give me 4 minus 20, which is negative 16, plus 29, which is 13. Okay, let's check f of 4, because that's f of b. Okay, the numbers are going to be a little bit bigger here. So 4 squared is 16 times another 4 is 64. Minus 4 times 20, so that's 80. So 64 minus 80 is negative 16, plus 29 once again is 13. So the conditions, or the hypothesis for Rolle's theorem, is met. We're good there. So if that's the case, then there has to be at least one value in between 1 and 4 such that the derivative equals 0. Well, let's find it. Part B. The derivative is going to be 8x minus 20, and someplace that has to equal 0. So if we add 20 to both sides and divide by 8, 20 divided by 8 will simplify to 5 halves. 5 halves, yeah. Which is the same as 2.5. So this is the c value that we were looking for, 5 halves. And that's definitely in between 1 and 4. So that checks out. It's in between the open interval 1 to 4. So let's illustrate it graphically. Okay, this is a parabola. And we know, let's see here, we know that the endpoints are 1 and 4. So 1, 2, 3, 4. Let's count by ones. If we plugged in 1, we got out 13. So we'll just call this 13 up here. And if we plugged in 4, we got out 13. Okay, now by symmetry, since those two things are on the same level, I know that the vertex has to be halfway in between there. Halfway in between 1 and 4 is going to be at 2.5. Lo and behold, 2.5 is going to be someplace over here. If you were to actually plug in 2.5, I think you actually get out 4. Okay, I did not do that on this one, but I think that's the answer. And then you would simply have this graph, that portion of the parabola between 1 and 4. And then you can clearly see you would have a horizontal tangent at 2.5. So it works out. But again, that's just a special circumstance of the mean value theorem. So the mean value theorem, which is actually a little bit nicer because it's only 2 things to know instead of 3, says the mean value theorem hypothesis, f has to be continuous. Spell that right, continuous, on the closed interval from a to b, and it has to be differentiable. On the open interval from a to b. Notice it doesn't say anything about the endpoints being equal, and in this case, they don't have to be equal. What it says is that if these 2 things are met, you get a continuous closed function, and it's differentiable on that entire interval, then there's going to be a number c, again, that's some x value in between the endpoints, such that the derivative, or the instantaneous rate of change at c, is the same thing as the average slope between a and c. So again, let's take a look at what that actually looks like. So here we have a curve. Okay, we are going to label the endpoints. This is a, This is b. Okay, in this case, they are clearly not the same y values, so Rolle's theorem isn't really applicable here. But what it says is that since it's continuous and closed, and it's differentiable in between the endpoints, which this clearly is, there's no corners or cusps or anything like that, no breaks, then the average slope between A to B, so whatever that slope is, and you can easily find the average slope between 2 points, it's y2 minus y1 over x2 minus x1, which is the same thing as f of b minus f of a over b minus a, same thing. That average slope has to be the same thing as the instantaneous slope at least 1 point in between A and B. So if I were to draw that exact same slope, I don't know if I can do that. I probably can't do it. I'll just go ahead and sketch this. Nope, I missed. So that is supposed to be exactly the same slope. It would be tangent to your curve right there because it's a derivative. And then you would have a point down here, C, in between A and B, such that these two slopes are exactly the same. And there could be more. There might be more than one of these, depends on what your curve looks like. But it's going to guarantee at least one will happen. Okay, so that's all that it really says. It says the average slope equals the instantaneous slope. Now let's think about what this is called. It's called the mean value theorem. Mean, meaning average. The average value of the slope. So it's the average rate of change, the mean value theorem is going to be the mean equals the instantaneous somewhere. That's all it is. The average slope will equal the instantaneous slope somewhere. Now, it does have to have these criteria. It must be a continuous function, and it must be differentiable, and it's got to be in between the two endpoints. It could be discontinuous someplace outside of our domain, but within our domain, whatever we're given, it has to be continuous and differentiable, and you would need to state both of those criteria in order to use the mean value theorem. Okay, let's go ahead and take a look at an example. So our example is, if f of x equals x to the fourth minus 5x cubed minus 33x squared plus 113x plus 50, long function. Find all the values of c and the interval from 0 to 7 that satisfy the mean value theorem. Okay, first of all, criteria. Does it work? Well, it is a continuous function because it's polynomial on a closed interval because they gave us the closed interval from 0 to 7. And again, it's polynomial, so it is differentiable on the open interval from 0 to 7. So the criteria is met. We can use the mean value theorem. And the mean value theorem says the average slope between the endpoints will equal the instantaneous slope. So the average slope, how do we find the average slope? Average slope is f of b, which is y2, minus f of a, which is y1, over b minus a, which is x2 minus x1. And remember, a and b are these values right here. This is a, this is b. Okay, left endpoint, right endpoint. So let's figure out these values. So we've got f of b, that's going to be the function at 7. That's going to be some big numbers to deal with. Minus the function at 0, that's an easy one, over 7 minus 0. So no, I did not do this without a calculator. I had to use a calculator to plug in 7, and you would end up with negative 90. 0, you can pretty much do without a calculator. That's going to give you 50, so minus 50 over 7. So that's going to be negative 140 over 7, which ends up being negative 20. So that's the average slope between the endpoints. Mean value theorem says that the derivative has to equal that slope somewhere, because remember, derivative is instantaneous slope. So the derivative, let's take the derivative. 4x cubed minus 15x squared minus 66x plus 113. And that has to equal negative 20. All right, this thing is a cubic. In order to solve this cubic, we need to get one side set equal to 0. So we're just going to add that 20 to both sides of the equation here, which is going to give us plus 133 on the right and then equals 0. And then you would have to try to factor this. This does not factor easily. There is a such thing as a cubic formula, just like that there is a quadratic formula. I have no idea what the cubic formula is. I don't even know if I've ever used it. Maybe one time, a long time ago in college or something. I don't know. It's not very commonly known. So we are going to use the calculator to figure this out. What you're going to do is you're going to plug that function into your calculator and then see where it crosses the x-axis. You might have to adjust your window. You might not. As a matter of fact, you won't, because I happen to know the values of these and they all lie within a standard 10 by 10 window. So what we would get, and the best thing to do is to do a second trace in your TI 83 or 84, and then do the 0 option, because it'll allow you to find the zeros. So just surround the 0 on the left and right, and it will give you the x value. You should get the x values here are negative 3.546. X is 1.665. And x is 5.632. But the question asks us, find all the c values on the interval from 0 to 7. So while these x values all make 0 on the derivative, there are only two solutions to this, because only two of these lie between 0 and 7. So those are our c values. Okay, the x equals the negative number is still a solution to the derivative equaling 0. It just wasn't in our domain, so that's not what they were asking us to find. So it's just two solutions in this case. All right. One more, actually very short problem, even though it's got a lot of words in it. So it says, two stationary patrol cars equipped with radar are 5 miles apart. As a car passes the first patrol car, its speed is clocked at 50 miles per hour. So you're doing fine. 4 minutes later, as the car passes the second patrol car, its speed is clocked at 55 miles per hour. Once again, seems like you're doing fine. Prove that the car must have actually exceeded the speed limit of 55 miles per hour. That's back when there actually were 55 mile per hour speed limits at some time during the 4 minutes. Now remember that because we're doing this in miles per hour, we have to change the minutes into hours. So 4 minutes is the same as 4 minutes out of 60, which is the same as 1/15 of an hour. So that helps. So what we know is that velocity is the change of distance over the change of time. Well, we can figure out how far we went and how long it took us to get there. So it says the two cars were parked 5 miles apart. So that really kind of tells you what your change in distance was. However, if you want to go ahead and plug it in, you know that you had gone, well, I guess it doesn't matter. We're just going to plug that in. As the change of distance was 5. The change of time, well, we went for 4 minutes, which is 1/15 of an hour, which is 1/15. So dividing those two things is multiplying by the reciprocal of the bottom fraction. So 5 times 15 is 75 miles per hour. So that tells me this person was flying in those 5 miles in between the two speed traps, and they noticed the police cars and slowed down appropriately, I guess. But that would be an example of the mean value theorem, because what we just did was we said that the average velocity, which is this, equals the instantaneous velocity, which is that one, somewhere in between the two. Now we are assuming that we do not stop anywhere or have any kind of non-differentiable function of velocity in between somehow. But that's pretty much what this is. So that's a really odd application of the mean value theorem, but it is an application. All right, good news is that is the only video. We kept it under 20 minutes, so enjoy.